right, I guess the goal for today is to discuss some progress on the third conjecture that I mentioned yesterday, which is on vanishing of cohomology, but in the special case of Shimura varieties. And that's really going to be most of what I talk about. So I want to state some conjectures and some results, particularly for unitary Shimura varieties. And then I plan to talk about the geometry of the Hodge-Tate period morphism, which already showed up in Sug Woo's talk, but which plays a key role in recent progress on this conjecture. And then I want to discuss sort of actual strategies of proof, and I will focus on two complementary approaches, one that is joint work of myself with Scholze, and the other one that's a more recent paper of Koshikawa. And finally, in the last part of the talk, I'll explain how this result gives rise to applications to local global compatibility. So the second conjecture that I mentioned yesterday, and not just for Shimura varieties, but really even for locally symmetric spaces attached to GLN over CM fields. And then further applications to modularity and potential modularity over CM fields. All right, so that's sort of the rough plan for the talk. And then, so remember the third conjecture would say that the non-Eisenstein part of the cohomology of a Shimura variety with, say, mod L coefficients should be concentrated in the middle degree. So rather than working directly with this and with the global condition, which is to ask for non-Eisenstein system of Hecke eigenvalues, which says that the associated L parameter is irreducible, I want to introduce a local condition at an auxiliary prime, which is somewhat related to this non-Eisenstein condition. It's not sort of, it doesn't imply it and it's not implied by it, but in certain cases, sort of you can ensure that both things are true. So, and they're somewhat related. So I want to take K as yesterday, a finite field of characteristic L. And so my coefficients are always going to be mod L. And then P is going to be a prime different from L. And if I look at a local field, capital L, and a continuous representation of the absolute Galois group of that local field, then I want to call that continuous representation generic if it's unramified. And if the eigenvalues, so it's an n-dimensional representation. So if I count eigenvalues of rho bar of the Frobenius with multiplicity, I would have lambda 1 through lambda n satisfy lambda I over lambda j is not equal to the cardinality of the residue field of L. And here I can put that or its inverse for I not equal to j. Okay, so that's one local condition that you can define for a local field. Then if I take F to be a number field and a continuous representation of the absolute Galois group of that number field, then we can say that a prime P different from L is decomposed generic for this representation if P splits completely in F. That's sort of the decomposed part. And then for all V dividing P prime of F, the restriction of this representation to the decomposition group at V is generic in the previous sense. And then we'll say that the whole global representation is decomposed generic if there is one decomposed generic prime. And if that happens, then by Chebotarev, you can show that there isn't just one, but there are really infinitely many primes that are decomposed generic for your representation. So you have lots of choices. All right, so this is going to be our local condition that we're gonna want to impose on our systems of Hecke eigenvalues or on the associated Galois representations. And I want to make some remarks about this condition. So the first thing is that the local condition, so in part one, when I say genericity or generic, this guarantees that any lift of rho bar to characteristic 0 corresponds to an irreducible or generic principal series representation of GLN of L. And so in other words, the case that you're really, you're excluding the case where your lift can be, say, like supercuspidal, but you're also excluding the case where, for instance, what you have is the induction of the trivial character from the Borel subgroup, which is reducible. And for instance, you see there non-generic representations, such as just the trivial representation, and you see generic representations, such as the Steinberg. So that's a case that we want to exclude. And that's exactly sort of the case where you would need the ratio of eigenvalues to be this residue field cardinality. And another way to think about this is to sort of view this condition, sort of rho bar cannot be, if you think about mod L Langlands, cannot be the L parameter of some non-quasi-split inner form of GLN, which I'll call GB to follow notation of Farg and Scholze, where B is some element of the Kottwitz set of GLN over this local field. So it's exactly a condition that will guarantee that these L parameters will not be in the image of some sort of non-trivial Jacquet-Langlands transfer. So they're in the image, they can be L parameters of representations of GLN, but they do not come from non-quasi-split inner forms of the group or of some Levy subgroup. And then I also want to comment that the decomposed generic is a global condition, and it's related to asking that rho bar has large image. But it's more of a group theoretic exercise to understand under what circumstances can you guarantee that a global Galois representation is decomposed generic. So if, so let's say, for example, if F is totally real and N is equal to 2, and I want rho bar to be odd, then the image of rho bar is, if the image is non-solvable, so inside GL2K is not a solvable group, then rho bar is decomposed generic This is a lemma that you can find in a paper that I wrote with Matteo Tamiozzo. However, you could take, I think it's possible to take an absolutely irreducible row bar, but whose image is, or at least the projective image is dihedral, and it's not decomposed generic. So it's not exactly true that this global condition of decomposed generic is exactly always implied by non-Eisenstein. It's a stronger condition. Okay. So we want to prove some version of the third conjecture from the last talk in the case of certain Shimura varieties under this condition on the Galois representation. So I want to, so this was terminology, and now I want to actually think about the Shimura varieties that we're going to consider for the rest of the talk. And they're going to be of PEL type A. So I want to take a PEL datum. Sorry, is there a question? So this is going to give rise to a Shimura datum, which I can call GX. And the point is that because we're taking a PEL datum of type A, this is going to be a unitary similitude group. And I want to take B to be a central simple algebra with center F, where F is some CM field. Okay, and for simplicity, the case that we're ultimately going to care about is the case where B is just F, and this involution star is complex conjugation, and V is some vector space of, say, even of dimension, let's say 2m for some integer m over F, and then this pairing here is some non-degenerate alternating Hermitian pairing. Okay, but so this is also going to give rise to a Shimura variety of PEL type, and I'm going to denote these Shimura varieties by SH sub k, where k inside of G of the finite adels is a sufficiently small compact open. And these Shimura varieties are going to live over some reflex field, which is a number field that I'm going to denote by E. Okay, and so we're interested in the cohomology of these Shimura varieties with mod L coefficients. So let's say I look at H star of these Shimura varieties. I mean, I could work with mod L coefficients or with ZL coefficients. It doesn't matter enormously. Yeah, let's say FL. It doesn't make a huge difference which one. So as before, I have a Heck algebra acting, and S is some set of primes that contains all the bad places and all the infinite places, some set of places of F, which contains all the bad places, all the places above L, all the places above infinity. And then using the notation from last time, I have this Heck algebra that acts faithfully on this cohomology group, where I'm suppressing the lambda because I'm working with constant coefficients. And the reason I'm working with constant coefficients is that I mentioned last time that, if you have this vanishing conjecture for some twisted coefficient given by some local system of some weight, you can always reduce this to the conjecture with constant coefficients as long as you allow yourself to increase your level at L arbitrarily. And we're not going to put any conditions on the level at L. And so the Hochschild-Serre spectral sequence then guarantees that it's enough to just consider the case of constant coefficients. Okay, and now I'm going to consider in here a maximal ideal. So a system of Hecke eigenvalues that occurs in the cohomology of this Shimura variety with mod L coefficients. And as in Sug Woo's talk, you've seen that this technique of Scholze for constructing Galois representations attached to torsion classes applies in this case. So, it sort of goes via the mod L or mod L to the n cohomology of Shimura varieties. And so as you've seen in Sug Woo's talk, it exactly constructs Galois representations attached to systems of Hecke eigenvalues that occur in the mod L cohomology of these kinds of Shimura varieties. In fact, it applies to Shimura varieties of Hodge type. And I guess you have to do some arguments at the end to really construct the Galois representations and reduce to the conjugate self-dual case. And when you have a unitary group, this is quite simple. And in fact, I don't know. You can even do it unconditionally using a base change result of Sug Woo. So let me just say that you get a global Galois representation, which is going to be, so let's say here, maybe I take V. I mean, it depends on what the dimension of this vector space V is, but I haven't introduced an N yet. So let me just say GLN, and it's going to be valued in, well, some finite extension of FL, but let me just say FL bar for simplicity. So such a Galois representation exists. I'm again cheating a little bit because I have a unitary similitude group. So technically the representation here might be this plus a character, but we're not going to care about the character. And so we only care about sort of this n-dimensional piece. And then one can formulate a conjecture, which is kind of like conjecture 3. From last time, but it's under this decomposed generic condition. And I mean, this is a global formulation where I look at a global system of eigenvalues and I look at the associated global Galois representation. One could also formulate it locally. And I'll mention this in a second, but in any case, this formulation is inspired by the formulation of Koshikawa. If rho m bar is decomposed generic, then the cohomology, and I wanted to simplify things, so I just took usual cohomology, but we really want to consider both cohomology with compact support here and usual cohomology. These Shimura varieties are typically non-compact, although there are cases where the Shimura varieties are compact, depending on your choice of PEL datum. For instance, the Harris-Taylor type of Shimura varieties gives you compact ones. So then you expect that the cohomology with compact support is supported in the middle degree and below. So I is less than or equal to D, which is the dimension of our Shimura varieties. It's varieties over this reflex field, say. And by Poincare duality, you also have the other inequality on degrees. Right, so these two are just related. If you prove any one of them because you're at finite level on your Shimura variety, you can use Poincaré duality to get the other one. Okay, and then in particular, if either your Shimura variety is compact, in which case usual and compactly supported cohomology agree, or M is non-Eisenstein, in which case, well, you can always describe the difference between cohomology with compact support and usual cohomology in terms of the cohomology of the boundary. And this amounts to understanding cohomology of locally symmetric spaces attached to Levy subgroups or parabolic subgroups of your original group. And what you see in the boundary can be shown to be reducible. So if M is non-Eisenstein, then after localizing at M, the cohomology of the boundary would vanish. And again, you get into a situation where usual and compactly supported cohomology agree. So either of these two things happen, then sort of H star with compact support of our Shimura variety with ZL coefficients localized at M is isomorphic to usual cohomology of the Shimura variety with ZL coefficients localized at M and is concentrated in the middle degree D. In degree D. And another thing that you can do is, because you actually prove this result first with mod L coefficients, and then you can prove it by some devisage argument with mod L to the n coefficients, and in the limit you get it with ZL coefficients. And as part of this argument, you also prove that the cohomology groups with ZL coefficients are actually torsion free. Okay, so this is the conjecture. And so this applies, the way that I've formulated it, this applies to PEL type A Shimura varieties. And under this decomposed generic condition, so under the assumption that there's some auxiliary prime that splits completely in your CM field, and where you have genericity at every prime above it in your CM.
I'm a bit confused because you were formulating a conjecture and then you explained arguments for proving it.
No, have I've just...
You said you prove it for by a devisage for Z model to the n, and then you also prove that there's no torsion. Can you...
Sorry. So what I mean is you have this conjecture and you can put it as a remark after the conjecture if you want, or you can put it as part of the conjecture. So as an immediate consequence of 1 and 2, if you also assume compact and non-Eisenstein, then you also get these things. So you can put them as part of the conjecture if you want, or you can put them as a remark after the conjecture. This is not how you prove. Sort of the hard part is to prove 1 and 2. So what I was describing was not how to prove 1 and 2, but how sort of once you have 1 and 2, you can also get it with mod L to the n coefficients. You can also get it with ZL coefficients. And you also deduce that the cohomology with ZL coefficients is torsion free.
Okay. How do you deduce that it's torsion free?
Well, there's a standard short exact sequence that you can write down, which is you look at sheaves like ZL goes to ZL under multiplication by L goes to FL. And on cohomology, this tells you that torsion in 1 degree is sort of related, is with classes. I am always, okay, now I'm doing it in my head, but it's related to ZL. So torsion in 1 degree is related to things that do not lift to characteristic 0 in another degree. And so, there's a bit of sitting down and working with this long exact sequence that you need to do, but you get it from this.
Okay, thank you.
I'm sorry, can I ask another question? So you're using this row and bar constructed by Scholze? But how do you expect this to be related to just the like actual representation coming from the cohomology of this Shimura variety?
So this is not, okay, so this is a good point. This is not the representation on the étale. This is not the representation on the étale cohomology of the Shimura variety as predicted by the Kottwitz conjecture, right? So this would be like the L parameter attached to rho m bar, right? So this relationship here is, rho m bar is uniquely characterized by the fact that at unramified primes, its Frobenius eigenvalues match the Satake parameters. And so then the question that you're asking is, what does this have to do with what you actually see on the étale cohomology of the Shimura variety? And I guess the answer is, well, in characteristic 0, there is this conjecture of Kottwitz that was mentioned in Morel's talk, mini course, right? So the Shimura datum has a Hodge co-character mu, and then from that, you form an algebraic representation, and you want to apply that to your L parameter, and that's what's predicted to occur in the cohomology of the Shimura variety. And so in some cases, like in the Harris-Taylor case, you actually see the L parameter in the cohomology of the Shimura variety, because you have this very nice like 1n minus 1 signature at one place and 0n at all the others. For other signatures, you would see, for instance, an exterior power or a tensor product of exterior powers. But I mean, my argument is that this rho m bar is more fundamental, right? Like this really knows about the Hecke eigenvalues in some sense. Like the other comment to make is that once you have, like, if you are able to prove this conjecture, once you know that your cohomology is concentrated in middle degree and torsion free, then, like essentially in many of these cases, we already know Kottwitz's conjecture. And because you're torsion free, you know Kottwitz's conjecture in characteristic 0, you also know exactly what the Galois representation is. But there is an interesting question there about how, I don't know, how like what you actually see on the étale cohomology of the Shimura variety versus what you see in terms of Hecke eigenvalues and how these things interact even in the torsion setting. Okay, so maybe I should have made this remark that, if we work with, let's see, should I make this remark now? Maybe. So one is, if we fix a prime P that splits completely in F, and such that KV, the level is full level, hyperspecial at GLN OFV for all V dividing P prime of F, then you can formulate a version of this conjecture, 3 primed, only using the spherical Hecke algebras at V dividing P and their systems of eigenvalues. So one could formulate, one could forget about the global Langlands correspondence, and one could just say, let's assume we have a prime that splits completely in F, and let's assume that it's sort of the eigenvalues at the different primes above it have this property that their ratio is never equal to P. Or maybe you have to think about how you would normalize it, because it's a condition still on the sort of L parameter. But assuming that I'm not making a mistake with the normalization, you put a condition like this, and then you say, so just in terms of these eigenvalues at some prime p, you would expect 1 and 2 to hold true. I guess the reason that I prefer to state it from a global perspective is that sometimes you can put conditions like large image, right? Sometimes you can say, this global representation, let's assume it's non-solvable. And then you're guaranteed that you have infinitely many primes that will work. And it sort of highlights the extent to which, if you're trying to get to this global conjecture that's non-Eisenstein, how you can try to reach it by putting various additional conditions on this global representation. But you can also formulate it from a local perspective, and you can look at this paper of Koshikawa and see this if you'd like. Okay, but again, this is about, say, Hecke eigenvalues or about the L parameter that is just attached to a system of local Hecke eigenvalues. So it's not typically about the étale cohomology of the Shimura variety. Right, and another remark that I wanted to make is that there have been results. So there have been results on conjecture 3 and 3 prime, maybe results sort of towards this kind of thing. So conjecture 3 is the non-Eisenstein case. Conjecture 3 prime is with a local condition, which in this case, is this decomposed generic condition at an auxiliary prime. But with other local conditions, there have been results of Lan and Su. So they prove it, in fact, without any condition on the system of Hecke eigenvalues, but assuming that they're in a sort of Fontaine-Lefy situation. So level prime to L and weight sufficiently regular and also small with respect to L. There's a result of Emerton and G. There's work of Shin. Yeah, that sort of, he puts a supercuspidal condition instead of a generic, right? Generic points towards having lifts that are irreducible generic principal series representations, whereas Shin looks at sort of a system of eigenvalues where you're kind of supercuspidal at an auxiliary prime, so in the other direction. And Boyer in the Harris-Taylor case, who's gone further than all of these. So maybe let's just say here, this uses sort of p-adic Hodge theory, integral p-adic Hodge theory, these two approaches. And supercuspidal condition instead of generic or decomposed generic. And Boyer sort of has gotten closest. So I think maybe under some relatively mild conditions, he actually proves conjecture 3, but in the Harris-Taylor case. And right, and for actually proving this conjecture 3, it turns out it's useful to think about the étale cohomology as well, and what you see there in Eichler-Shimura relations and things like this. Okay, but now the focus of the talk was going to be the results in my joint work with Scholze and in this more recent paper of Koshikawa. So I want to state, because that's sort of the most general in the direction of this conjecture 3 primed that I stated. And also sort of the most promising technique for generalizing both to getting the full conjecture and also to sort of getting the conjecture for Shimura varieties attached to other groups or with maybe other conditions at the primes. So the original approach that was joined with Scholze had more technical assumptions, and Koshikawa's result is cleaner, but maybe I'll just state them both together. So if the Shimura variety is compact, or B is F and V is F to the 2M, and the associated unitary group is quasi-split. So quasi-split at all the places, the conjecture is true. So in the compact case, or essentially in the case of sort of UMM Shimura varieties, I mean, the group has to be quasi-split, but in particular, this means that the signature at infinity, in this case, would be MM of our unitary group. Okay. And more remarks about this. First thing is that sort of they both use, so both approaches use the geometry of the Hodge-Tate period morphism, which I'll talk about in a second. And it's essentially saying, well, sort of the approaches are complementary. I won't write this, but let me just say it for now. In the sense that it turns out that you can write Newton strata in Shimura varieties as roughly some kind of product of Igusa varieties and Rappaport-Zingg spaces. And the original approach that's joined with Scholze sort of shows that the cohomology of Igusa varieties vanishes. And Koshikawa's approach shows that the cohomology of Rappaport-Zingg spaces under this genericity condition vanishes. And Koshikawa, in addition, also needs semi-perversity result from my joint work with Scholze. So sort of he goes via Rappaport-Zingg spaces, but also needs an ingredient that's obtained in my joint work with Scholze. And this leads me to the next thing, which is my PhD student, Mafalda Santos, is working on the full conjecture and expect to sort of have this available in the sort of near future, let's say. So it definitely has all the ingredients in place on this full conjecture. So this is for PL type A Shimura varieties, and under this assumption that you're working with a prime that splits completely in F. And this is via, I mean, essentially Koshikawa's method is very general. And the only thing that is needed in order to make the method go through for all PL type A Shimura varieties is, when P splits completely, is that you need to generalize a more geometric semi-perversity result from this paper with Scholze. And that's what Mafalda is doing. So she's studying the geometry of compactifications of PL type Shimura varieties and Igusa varieties and generalizing this semi-perversity result. And my understanding is maybe there are other people who are thinking about other contexts. So maybe, you know, like unitary groups where the prime is not split. So you really have a unitary group rather than GLN, or GSP4 might also be doable with similar techniques. Yeah, I'm not sure about GSP2N yet. Via this and Koshikawa approach. All right. So any questions? I went a bit further, a bit longer than I wanted to, but I guess it's good to at least state things clearly. Are there any questions before I move on to the next part of the talk?
Speak up.
What is semi-perversity?
Well, this is essentially saying that a certain sheaf on the Hodge-Tate period morphism is in perverse, sort of in D greater than or equal to something. So, you know, perverse, you can define a perverse T structure, and that consists of two full subcategories, a D greater than or equal to, say, 0 or some other integer, and a D less than or equal to. And their intersection is the heart of the T structure, and that's the category of perverse sheaves. So if only one of these is satisfied, then that's what semi-perversity means. So it's saying, yeah, something like this. Okay. So if not, I want to talk about the geometry of the Hodge-Tate period morphism. And I think since I went a bit slower than I wanted to, I think my plan is to just continue going at whatever speed where I get to say what I wanted to say. And then, you know, if I don't get to talk about applications, then you're welcome to ask me about them in the Q&A or, you know. I feel like, yeah, I don't want to rush it. So we have this Hodge-Tate period morphism that showed up in Sug Woo's talk. Let's say like this. And I'm just going to denote this flag variety by FL, but just to remind you, this depends on your group that gives rise to the Shimura datum and on the Hodge co-character mu. So it's really sort of G modulo a parabolic determined by the Hodge co-character. Okay, so this is maybe pi Hodge-Tate. And then there's also toroidal compactification and minimal compactification of the Shimura variety. And let's maybe say that this is pi. No, let me not use star because this can be confusing if you apply it to a morphism. Let me say min, tor, and then there's a min and a tor. But for the purposes of the talk, I really want to sort of give you some sense for what's going on in the case of compact Shimura varieties and not really talk too much about compactifications. But just to say, you know, everything does extend. And at least as diamonds, we have SKP, where I can put here min or tor, or I can just leave it. This is the inverse limit over the level at P of the Shimura varieties viewed as adic spaces. Okay. And the maybe next thing to say is that there exists a Newton stratification both on the Shimura varieties and extending to compactifications and on the flag variety. So there exists Newton stratification on FL, where you can decompose this as a disjoint union over elements of the Cotwood set that are bounded by mu. These are locally closed strata. And sort of the way that one even understands closure relations. So if I take a stratum and I look at its closure, then this is a disjoint union over all elements that are bigger than it in the Bruhat order, FLB primed. Okay, and this is actually a more recent result from last year of Feynman. the fact that you really understand the closure relations among strata. Okay, so what do I want to say about it? You can identify this flag variety with a minuscule Schubert cell attached to this Hodge co-character, which is a minuscule co-character, inside the BDR plus Grassmannian via an isomorphism known as the or it's a special case of something called the Bialinitsky-Birula decomposition. Maybe I won't write this, but this Grassmannian has a map to Bun-G, and because you can identify this flag variety with a minuscule Schubert cell in it, it also has a map to Bun-G. But another way to think about it is this flag variety has over it living sort of a family of G bundles over the Farg-Fontaine curve. And that's what gives the map to Bun-G. And the way that you construct this family is you can take a trivial family and then you modify it along with the filtration that is sort of parameterized by the flag variety somehow. So anyway, there's a construction like this. And the Newton stratification is then pulled back from the Newton stratification on Bun-G. So it's something that's defined, you don't need the Shimura variety in order to talk about it. You can work purely locally and define this, but at the same time, it's compatible on rank 1 points with the Newton stratification on the Shimura variety. Which is, so compatible, maybe here to clarify, sort of under pi Hodge-Tate, right? So this pi Hodge-Tate morphism has various nice properties, and one of the nice properties is that the two notions of Newton stratification, at least on the level of rank 1 points, are compatible. It's sort of more subtle what happens on higher rank points, but let me just, in order to orient you, so the element that's maximal in the Bruhat order would be the mu ordinary one. For instance, if we're working in the setting where P splits completely in F, we actually have an ordinary locus. So the maximal element in the Bruhat order will be the ordinary one for us. And that would be a closed stratum according to these closure relations. And that's what, let's see. Just write it differently so that you see. So FL ord is closed. And in fact, this can be identified with the points that are already defined over QP of the flag variety. So the reflex field here is actually just QP. And the ordinary points are this. And then FL basic is open. And so, for instance, in the case of the modular curve, the flag variety is P1. You remove the ordinary locus, which is the QP rational points, P1 of QP, and then you're left with the Drinfeld upper half plane, which is the basic or supersingular locus in the case of the modular curve. And then more generally, you have more Newton strata. But yeah, we understand at least their closure relations. Although they're not sort of, it's very hard to give a description of what the Newton strata actually look like. For an arbitrary element B. Okay, right. And so the basic locus is open, the ordinary locus is closed and zero dimensional. Then I claim that the next thing to do is to understand the fibers of the Hodge-Tate period morphism over a fixed Newton stratum, or even the sort of the structure of the Hodge-Tate period morphism over a fixed B. And in order to do that, one needs to talk about Igusa varieties and Rappaport zinc spaces. So Igusa varieties.
Well, can I ask a question?
Yeah.
just for this Newton stratification, does it depend on a chosen choice of P and baked to be added space, or it's already defined like globally?
Sorry, I didn't understand the question. Does it depend on a choice of what?
Yeah, I mean, is this stratification local or is it global?
It's local. Yeah, so the stratification on the flag variety is local. So you do not need to talk about Shimura varieties, which are global objects. You don't need to talk about abelian varieties. You can just view sort of FL as some kind of moduli of local shtukas and have a map to Ban G. And from that, you get your Newton stratification. So yes, so on the flag variety, it's a purely local thing.
Okay, thanks.
Okay, so to talk about Igusa varieties, I need to talk about the integral model of the Shimura variety. So I can look at, this is going to be my special fiber, where I'm taking Kp to be hyperspecial. So it's the product of GLN OFV in this case, which is really a product of GLN ZP. All right. And so there is a Newton stratification already here, but for B in this Kottwitz set bounded by mu, there is a non-empty Newton stratum. But I want to be more precise than that. I want to say that you can find a p-divisible group with extra structures, sort of PL structures that are predicted by G. So I'll say p-divisible group with G structure, XB over FP bar, which has as its associated isocrystal with G structure is B, and at the same time, it's compatible with the Hodge cocharacter mu, which means that it satisfies something like the Kottwitz determinant condition for sort of as predicted by mu. And so it's something that could occur as the p-divisible group of some abelian variety that's parameterized by this Shimura variety. And then associated to this choice of p-divisible group, we can consider an Oort central leaf, which a priori is just a subset of points on the Newton stratum, because we're already sort of fixing the isogeny class of the p-divisible group. But we want to consider specifically the subset where there exists an isomorphism of the universal p-divisible group restricted or pulled back to a geometric point above our point. There exists an isomorphism compatible with extra structures with this XP. So the Oort central leaf is a priori a subset, but it's really a smooth and closed subscheme of the Newton stratum. So this is called Oort central leaf, where at least on geometric points, the isomorphism class of your p-divisible group is constant. So for example, over the ordinary locus is itself a central leaf, because at every geometric point on your ordinary locus, the p-divisible group just splits as a product of an étal part and a multiplicative part that have fixed rank. But sort of globally over the leaf, you don't have just a constant p-divisible group, because you have some extension of the étal part by the multiplicative part. So similarly, over a more general Oort central leaf, sort of locally at every point, you have a fixed p-divisible group, which you can also ensure has a slope decomposition, but then globally over the leaf, the structure is more complicated. And this is where you introduce the Igusa variety that trivializes the p-divisible group globally over the leaf. So the Igusa variety is a profinite cover of the leaf. And I'm considering the case where we're taking it to be a perfect scheme. And it's the universal cover which trivializes sort of the universal object, which trivializes the p-divisible group that lives globally over this leaf. So there exists an isomorphism between the p-divisible group pulled back to the Igusa variety and our fixed p-divisible group pulled back to the Igusa variety, which is compatible with G structures. And you can think of this as sort of something that you can do in two steps. In one step, for instance, you would trivialize every piece of the slope filtration. So for instance, over the ordinary locus, you would want to trivialize the étale piece and the multiplicative piece. And then you also want to split, so globally, over the entire space, you want to split the slope filtration. And you can achieve that by going to perfection. So it's sort of first a profinite étale cover that trivializes graded pieces of the slope filtration, and then going to perfection, which amounts to splitting all the sort of extensions of p-divisible groups of different slopes. So this is, these Igusa varieties are objects that are, well, originally introduced in the work of Harris and Taylor, and then later defined more generally by Mantovan. And of course, the work of Oort and also Oort and Zink plays an important role in sort of defining them and sort of seeing that they're well behaved and that you really have first, you know, this kind of profinite étale cover, and then that taking perfection amounts to trivializing the whole group and so on. Right. And one nice thing that I won't write down, but I think it's a fun fact about this, is that so the leaf depends on your choice of p-divisible group XB in its isogeny class. And so the Newton stratum, you can think of it as having a foliation by different central leaves corresponding to different choices of XB in the same isogeny class. But the Igusa variety turns out is sort of, if you construct Igusa varieties over different leaves that are attached to the same sort of, that are in the same isogeny class, so still for the same B, then they end up being isomorphic. So the Igusa variety doesn't depend on the particular choice of isomorphism class of p-divisible group. It only depends on the isogeny class, so only depends on this element B. And in fact, it doesn't even depend on the Hodge co-character mu, in the sense that you can show in certain instances that Igusa varieties that a priori come from different Shimura varieties end up being isomorphic. And those are sort of instances of geometric Jacquet-Langlands. Okay, so it turns out, so what I really want to work with is maybe, I'll call it IG pre-perfectoid, which is going to live over SPA QP breve, CP breve. So because you have a perfect scheme over FP bar, you can lift it to characteristic 0 in a canonical way using the Witt vector functor. And so you can get a formal scheme over SPF of ZP brev. And then I'm taking the adic generic fiber of that. Yeah, so these are the objects that we're going to be interested in, which are going to be it turns out they're going to be pre-perfectoid spaces. So if I base change to a perfectoid field, they're actually going to be perfectoid spaces. Okay, then I want to briefly introduce Rappaport-Zink spaces. They've sort of come up at this summer school already. That's why I don't want to spend a lot of time on them. But so morally, they are moduli of local Stukas. But from this perspective, it's actually useful to have a moduli problem that's sort of closer to what we see when we look at the integral model of Shimura varieties and so on. So MB over SPF ZP breve is a formal scheme with the following moduli theoretic description. So roughly a moduli space of p-divisible groups, but let me be more precise. If R is a ZP breve algebra on which P is nilpotent, then MB of R is the set G rho, where G is a p-divisible group with G structures. Over R, and rho is a quasi-isogeny from our fixed p-divisible group, mod P to G mod P. So this is actually a quasi-isogeny. And of course, these tuples up to some notion of isomorphism. And both when you define Igusa varieties and when you define Rappaport-Zink spaces, you have to be careful about sort of, like writing things down and what does it mean to commute with G structure and what's a nice, what tuples are considered isomorphic and so on. I don't have time to do this, but it's important to do it carefully so that at the end, you get sort of a correct result. So I take MB to be the adic generic fiber of this formal scheme, and MB infinity to be the sort of the version where I add infinite level at P. And this is also going to be a pre-perfectoid space. So this is pre-perfectoid over QP breve, where I join Pth power roots of unity. And it also admits a local version of the Hodge-Tate period morphism, which comes from the Hodge-Tate filtration on that you can see on the level of p-divisible groups. And okay, these Rappaport-Zink spaces actually have two kinds of period morphisms. So there's the Hodge-Tate one, and there's the Grothendieck Messing one. The Grothendieck Messing one is about the filtration on de Rham cohomology rather than on étale cohomology. So it's important to keep these separate. But that's the one that I want to consider. And then the key result, so the reason I've been introducing all these objects is to state the product formula. And I'll just say there exists a Cartesian diagram of diamonds. And some things are going to be a little bit vague because I don't have time to define them completely precisely, but it's as follows. So you have the flag variety, and you look at the Newton stratum corresponding to some B. So this would be for any B and BG mu. You have the Shimura variety with infinite level at P, and I want to consider the good reduction locus. So if your Shimura variety is compact, then it doesn't matter. It's you can pretend I didn't say anything. If it's non-compact, then there's something that one needs to do. So you have to take the adic generic fiber of sort of the formal completion of the integral model along its special fiber. And you get sort of the good reduction locus. And you want to take also the Newton stratum corresponding to B, and you have to define this carefully so that you really get an adic space. But it's roughly the Newton stratum corresponding to B in the Shimura variety, at least in the compact case. And this is just the restriction of the global Hodge-Tate period morphism that sees this Hodge-Tate filtration on the abelian variety, or the relative position of that. There's the infinite level Rappaport-Zink space with the local version of the Hodge-Tate period morphism. And then it turns out that over here, I could take a product of the Rappaport-Zink space with the Igusa variety. The one that's viewed as an adic space over SPA, QP breve, ZP breve. And this maps down here, and this is Cartesian. Right, so this is saying that up to, going to the Rappaport-Zink space, so going from this Newton stratum in the flag variety to the Rappaport-Zink space via the local Hodge-Tate period morphism. If you do this, you unravel the Newton stratum on the Shimura variety as just a product of an Igusa variety and the Rappaport-Zink space. And this is an infinite level version of the so-called Mantovan product formula. She already saw this kind of phenomenon, but sort of she worked with integral models of Shimura varieties at finite level, and then it was less clear. So one could show that Newton strata are covered by products of Rappaport-Zink spaces and Igusa varieties, but it was less clear what the overall structure was. So I think this is cleaner. And another thing to say is that we can understand one of the arrows really well, namely this arrow. This is a Pro et al. Torsor for the group GB tilde in the notation of Varrick-Scholze. So you see that this Newton stratum in the flag variety is actually quite close to the Rappaport-Zink space. And this GP tilde is sort of a thickened version of just the group GB, which is an inner form of a levy of your original group G. Okay, so something like this. So the other side is also a torsor for GB tilde because the diagram is Cartesian. And let me just say that there is also a cohomological consequence of this. Let's see if I can. Already in Mantovan's case, she had a cohomological product formula for the cohomology of Shimura varieties and Newton strata and in Shimura varieties in terms of Rappaport-Zink spaces and Igusa varieties, and this has been used to understand the global Langlands correspondence in this conjugate self-dual case. But one can also deduce it from this infinite level version. And you can see the deduction, but it's an argument that's very close to Mantovan's original one. Cohomological, well, at least in spirit, product, cohomological consequence. You can look at this paper of Koshikawa. R gamma, or maybe I'll say that. The cohomology of Shimura varieties, so R gamma, compact support of the Shimura varieties. I think it's with compact support of the Shimura varieties with, say, infinite level at P and with FL bar coefficients has a filtration, which I mean in the derived sense. So rather there are a lot of distinguished triangles by cohomology of Igusa varieties with mod L coefficients, which you want to view as a representation of GBQP. And direct product over locally constant functions with compact support over GBQP with the cohomology of the Rapport-Zingst. So, I mean, this just, I guess, you know, this arrow over here is a torsor for GB tilde. And when you take a Tal cohomology with mod L coefficients, somehow the pro-unipotent part of GB tilde goes away. And just think of GBQP as contributing. And then essentially you want to say that the cohomology of the Newton stratum is a product of the cohomology of the Rapport-Zingst space and the cohomology of the Igusa variety. But because you have this, you know, you have to go to MB infinity from FLB in order to get this product decomposition, then you have to take the product over a representation of GBQP. And so that's what's happening here. So it's sort of saying it's a twisted, right? Like it's I don't know, a fiber bundle, and we know the fiber bundle structure. And if you think about what's going on, you can at least find it plausible that such a formula exists. And now, sort of the approach in joint work with Scholze is that, say, if I localize at a system of Hecke eigenvalues here that is decomposed generic, then one kills this part, assuming that we're in a situation where GB is not quasi-split. Maybe even it's enough to even say generic. And so we just have this genericity condition, and GB is not quasi-split, and that can be used to show that the cohomology of the Igusa variety vanishes. That uses the work of Shin to compute the cohomology of Igusa varieties, at least alternating sum. So I'll use this notation for the alternating sum of cohomology groups of Igusa variety with QL bar coefficients and localized at M. And then in Koshikawa's approach, instead, what one does is, again, under this assumption that M is generic and GB is not quasi-split, one instead sort of kills this part. So this is Koshikawa. He proves a local vanishing theorem, which maybe I'll state precisely so that you can see what it's supposed to be. L over QP, finite extension, G be mu a local Shimura data, such that G is a product over I and I of GL and I over L. So it's just general linear groups. And K is taken to be just the product of maximal compact subgroups GL and I OL inside G of L. And then one considers the Rapport-Zingst space MK. So with sort of this full level, which you can also refer to as a local Shimura variety. And then he proves the theorem. So we assume L is not equal to P. And if sort of M is in the local Hecke algebra, acting on the cohomology with compact support of this Rappaport-Zink space with ZL coefficients, and such that the L parameter, rho M, is generic, and GB is not quasi-split, then the cohomology localized at M actually vanishes. Right, so that's the result that he proves. And so he, if you have the product formula to describe the contribution of a Newton stratum to the cohomology of the Shimura variety, then that shows that after localization at something generic, and when GB is not quasi-split, then this second part of the product formula, the cohomology of the Rappaport-Zink space or the local Shimura variety, vanishes. Right, so these are the two approaches. And you see why I'm saying that they are complementary. It's nice, in fact, that in many cases you can show that both things vanish. Let me just say that the idea of proof so the cohomology of the Rappaport-Zink space has an action of this Hecke algebra. It also has an action of this GBQP, where GB is an inner form of a Levy subgroup of your original group, G, which is a product of general linear groups. And then what he shows is that, well, let's say if we look at it with FL coefficients or FL bar coefficients, whenever pi is an irreducible, smooth representation of, and maybe I'm working over a local field L, so GBL. Then there is a Langlands parameter, there's an L parameter, phi pi, which is constructed by Farg-Scholze. And this, in the case of general linear groups, the L parameter constructed by Farg-Scholze is actually known to be compatible with the classical local Langlands correspondence. And so because of this, it's not too much work to show that if GB is not quasi-split, then this is not generic, right? This is, I mentioned initially that this genericity condition is exactly cooked up so that, the image of local Langlands from non-quasi-split forms misses those generic parameters. On the other hand, if pi is an irreducible subquotient of HI of this Rappaport-Zink space, well, we're localizing at a system of eigenvalues, but the system of eigenvalues is for the action of GLN or GLNI of L. So one needs to show that the Langlands parameter attached to pi is the same thing as the L parameter attached to M. So there's some compatibility between the action of G of L and the action of GB of L than one needs. If one can show these two things, then one can conclude, right, that if rho m is decomposed generic, then the only choice is for the cohomology to vanish. So this uses really sort of the work of Schulze in a more significant way. So this uses excursion operators. And the action of the spectral Bernstein center and the fact that this is compatible with excursion operators. So sort of the hard thing is to show that these parameters agree. Okay, so I'm going to finish very soon. I'll just say that so far, both of these approaches show that when M is generic and GB is not quasi-split, the contribution of the Newton stratum vanishes. Now, you need decomposed generic to show that there's only one stratum for which GB is not quasi-split, namely the ordinary one. If you don't assume that the prime splits completely in your CM field, then you can have lots of Newton strata that still survive. So that's why you need decomposed generic. And then you need semi-perversity in order to control the cohomology of the ordinary locus and say that sort of that occurs in, say, the middle degree and above. And then using various arguments, you can show that sort of the, I don't know, kind of cohomology with compact support is then in the middle degree and below, and so on. So you need something to also just control the contribution from the ordinary locus. And this has to do with the fact that the Hodge-Tate period morphism, at least when you extend it to a compactification of a Shimura variety, is sort of behaves in some way like a profinite morphism in the sense that it's both aphenoid and partially proper. And for that reason, it sort of will send the constant sheaf on the Shimura variety to a sheaf that is a shifted perverse sheaf downstairs. Right. So let me just finish here actually. And yeah, if there are questions, I can address them during the Q&A. Thank you.
Any questions? Yes.
Yeah, very short questions about the notation. So in this diagram of Mont Van product formula, in the left bottom, what's the circ means here? I didn't follow that part.
So it means that, okay, if you were working with a compact Shimura variety, then you wouldn't need to put it there. So you don't have to worry about it. If you have a non-compact Shimura variety,
sorry, perhaps you can repeat the question, please?
Oh, repeat the question?
Yes.
The question seems to be that if I look here, what does this little circle mean? And I guess my answer is that it means something like good reduction locus. So when you have a compact Shimura variety, you can ignore it. If you have a non-compact Shimura variety, there is a difference between sort of starting out with a Shimura variety as a scheme, say over QP, and then viewing it as an adic space, versus looking at its integral model over ZP, taking the formal completion along the special fiber, and then taking the adic generic fiber of that. So like moduli theoretically, roughly, if you just take your scheme and view it as an adic space, then you can sort of parameterize points that correspond to abelian varieties that have bad reduction, that do not reduce to abelian varieties, but to semi-abelian varieties over ZP, or do not extend to, only extend to semi-abelian schemes over ZP. But if you take the adic generic fiber of the formal completion, then the points you're parameterizing are the ones for which the abelian varieties have good reduction. And so the circ means good reduction locus.
Okay, thanks.
Was that question? Yes?
Yeah, in the end, you talk about the normalization of to the maximum idea of the cohomology of Rapport link space, but to my understanding, I think vanishing space is a purely local object. Where comes the action of global Hecke operators?
Well, that's right. So that's true. Maybe I should have used slightly different notation. Yeah, I should have. Sorry, I was running out of time, and my notation wasn't great. But let's say here M primed, and let's say here I have M primed, and this is now a local. So I'm just looking. I have fixed my prime P, where I know I'm decomposed generic, so I know it splits completely, and it has this property on eigenvalues. And then I just consider those eigenvalues on the, I guess, okay, maybe I would need to be at finite level, but roughly, this is the idea, right? That I want to just look, like when you work with the Rappaport-Zingst space, you don't need to carry around the full global Hecke algebra. You can just carry around the Hecke operators at the primes that you are interested in. So
One more short question.
Yes, can you elaborate a little bit more about this these closure relations to the Newton strata, because they seem precisely the other way around as in the special fiber of somehow finite level varieties.
Sorry, I should say more about what? About closure relations or what?
Yes, these closure relations between the Newton strata seem to be precisely the other way around than in the special fibers of Shimura varieties.
Yes, that's right. They're exactly the other way around than in the special fibers of Shimura varieties. This is something that's very confusing and mysterious at first, and it's really crucial to make all the arguments work. Actually, I would recommend asking, if he's there, Matteo Tamiozzo. I think he's thought quite a bit about what happens and maybe has an example with elliptic curves in the setting of the modular curve that explains sort of how things can degenerate, how families can degenerate so that the closure relations look the way that they do.